All right, so back to this here, ladies and gentlemen. So we note that in this picture here, if this picture were to be drawn properly to scale, this would be the case. DC is greater than BD is greater than BC is greater than AC is greater than AB. Now, of course, this does not simply mean, this tells us relative side lengths. It doesn't tell us actual side lengths here. So, one may be tempted to say, wait a minute, okay, I can just pick any numbers that satisfy this here and that are all positive because we want these all to be lengths, and it should work. So I can have something like this, 5, 4, 3, 2, 1, for instance, right? So I can go into my picture, say DC has a length of 5, then BD has a length of 4, BC has a length of 3, AC has a length of 2, and AB has a length of 1 here. So, we could have something that looks like this here. Now, if you're paying attention and if you're looking very keenly here, so, watch carefully here, you'll note that there's an issue with this, right? So one of the things you may notice is that this 3, 4, 5 here, some of you may know that there's a right triangle. So first off, that can't work because there's no right angles here. But second, the more important thing here is this. Take a look at what's going on here. You see a 1, a 2, and a 3. If we were to try to draw a triangle with side lengths 1, 2, 3, it's actually going to collapse on itself, right? You can actually model this yourselves with sticks or straws or something like that here. So we note that this is the case here. We kind of don't have that. And some of you already may know about this thing called the triangle inequality, and that's going to be what we're going to be looking at here, okay? So, we're now going to focus on what is known as the triangle inequality here, ladies and gentlemen, okay? So, the triangle inequality in words is pretty straightforward here, right? So, the key for that was that you want to make sure that two sides have to be greater than a third. But not specifically any two sides here, not specifically two sides themselves, but we want their sum. So, we can say that the sum of the lengths of two sides of a triangle is greater than the length of the third. Okay? So we can kind of write it like this here. Now, for a triangle here, if you have ABC as your side lengths here, note that this actually means 3 inequalities here. It's not just a single inequality. So we can say that any two sides, A plus B is greater than C here, but also we can say that A plus C is greater than B here, and then we can also say that B plus C is greater than A. So notice that the most important part about this here is you want to make sure that all these are true at the same time. So it's not enough to just have one of these to be true or two of these to be true. For a triangle, if A, B, and C are the lengths of the sides of a triangle here, you have to ensure that all of them have to be true simultaneously here. Okay? And that's the key for this problem. All right. So, of course, just like any other good theorem here, we should prove this theorem. And I'm going to go ahead and prove this particular theorem here. And it turns out to work really, really nicely like this. So, I will have a copy of this in the Google Classroom for you. And I ask that you try to fill this in, fill it in along with while I do so. But again, try to reason it out on your own. There is enough information I've left behind here for you to figure out what's going on. Okay? So, remember the goal here is to prove AB plus BC is greater than AC. Okay? Pretty straightforward. That's a pretty straightforward goal. Okay. So we're going to extend AB out through B to a point D such that BC is equal to BD. That seems pretty fair, right? And again, that's going to be our preliminary stuff. That's what we're going to do at the beginning. Therefore, the angles blah and blah are congruent and thus have the same measure. Well, that seems pretty fair, right? We now have an isosceles triangle here, so it's pretty fair that these two angles have to be the angles opposite the congruent sides have to have the same measure here, right? So we can mention this. So therefore, the angles BCD and BDC here are congruent, right? I think we can say that, and thus have the same measure. We can therefore claim that the measure of angle ACD is greater than the measure of angle BCD here. Now, if we look at ACD, wait a minute, well, that looks like it has BCD in it, so that means we can conclude here, we know that BCD is a part of a whole, so we can mention that here. So we can say that the whole is greater than any of its parts. Mm-hmm. Now, here, notice that gives us this here. ACD is greater than BCD. But since we know BCD matches BDC here, right? We know that. We can therefore say ACD is bigger. We can swap this out and say the measure of angle ACD is greater than, in this case, the measure of angle BDC. Alrighty, so we're in good shape, ladies and gentlemen. This is looking pretty good. So now our focus is going to be turned to triangle ACD, the big triangle here. If we look at the big triangle, let's go back up here. So this big triangle here, we now know that ACD is bigger than BDC here. That makes sense. So that means we know that in this situation, because if we ignore BC here, we can see that in this case, AD being opposite the bigger angle is going to be bigger than what's opposite this smaller angle, which is AC here. So in this situation, we can now conclude that something like AD, right? So we know that AD is going to be greater than, in this case here, what's opposite this green angle on top, AC, since, well, let's see, let's go ahead and write this out here. Since in a triangle, the longer side is opposite the larger angle. However, now this is where this is where it goes here. However, we can write that AD is equal to blah plus blah. Notice how what's going on in this picture here. AD has been broken up into two pieces, right? AD was an extension of a side here, so it's going to be the smaller pieces together. So we can write this as AB plus BD. By partition postulate, right? There's our good old partition postulate comes again here. Okay? So now we have AD here is equal to AB plus BD. Okay, that makes sense here. But based on previous information, we can rewrite it as AD equals what? Well, there was one piece of information we haven't used yet. And if you look back here, it's right here. BC is equal to BD. So I can swap that out here, right? Because remember, the goal is to show that AB plus BC is greater than AC here. We kind of have AD is greater than AC. AC is on the right side, the correct side of the inequality here. And I've got AB. So I got to get rid of BD and put BC in its place. So I can do that, right? We can write AD equals AB plus BC here, right? Therefore, well, let's see here. So now we know AD is greater than AC, so I can substitute it in. Therefore, by substitution, postulate, we can say that AB plus BC must be greater than AC, and we're done. And the proof is finished. Well, not quite. The proof is almost finished. Because remember that, you may note, wait a minute, I've only proven one thing here. I've only proven that AB plus BC is greater than AC. I haven't shown that for the other things here. Remember, the triangle inequality requires all three at the same time. So in this case here, I kind of have to also show AB plus AC is greater than BC. I also have to show that BC plus AC is greater than AB. But the nice part about this is that, well, all I got to do is just reproduce this diagram, but just flip it, right? I can just, I extended AB out through a point like this here. To finish one of the other things, I can extend BC so that we create an isosceles triangle here. I can, extend AC to create an isosceles triangle as well. So notice that basically, even though the proof isn't done here, we can just basically use an almost identical argument here by just simply extending the right pieces and get ourselves the rest of the proof here to show that all three of the inequalities must hold. And therefore, this triangle inequality here has to hold. The nice part about the triangle inequality, ladies and gentlemen, is that because it's well known and it is a named thing, you can actually just call it by name. So you can say that this has to be true because of the triangle inequality.